Good. So today we'll be looking at some explicit list decodable codes. So traditionally speaking, I mean, if it was a coding theory course in general, I would have started off with unique decoding algorithms, etc., and then slowly proceed to list decoding. Whereas here, list decodable codes are going to be far more closer to the sort of objects we are studying. So I'm going to jump right into list decoding. But you can stare at the algorithm that we'll see today and then realize that basically the same technique will give unique decoding also. Anyway, when we get to the algorithm, I'll tell you. But let's look at some recap. Okay, so we were talking about codes in general last class. And we were referring to codes as just some via an encoding function, where you're given some message space capital N, and you're mapping it to some sigma to the n hat, where sigma is the alphabet that you're dealing with. And typically, sigma turns out to be some finite field. And so it's usually like a power of a prime that sigma has. And the rate is in some sense is like trying to capture how much loss do you have in this encoding map. So you're counting the information present on the message side versus the ambient potential information present on the code side, and sort of saying among the ambient information, how much is actually corresponding to your message. So you need to count this correctly. And this is one method, but typically when you're dealing with sigma to the k to sigma to the n, or some if your encoding function is of the form sigma to the k to sigma to the n, then the rate just becomes k over n. So then things are quite clean. And we were talking about this notion of distance of a code, which is you collect all possible pairs of code words, and amongst all possible pairs of distinct code words, you find out what is the pair that is closest, and what's the distance of the closest pair. Okay, and we will use capital delta to denote the unnormalized distance, that is the actual number of coordinates. But sometimes you might just use small delta of c to just denote the fractional distance that you just divide by the block length. All right. And we had a notion of unique decodability, which was to basically say that, you want to say no matter what received message you get, like if you draw a ball of radius delta around it, there can be at most one code word. There may be the case that there are certain received messages that this ball contains nothing. But the intuition is that you are imagining that a code word was sent through some channel and an adversary decided to go and change delta of the coordinates. And so what you end up seeing is the received word, and you want to know, can I disambiguate the message by just looking at the received word? And this is the right notion that you should be studying in that regard. And we also looked at the list decoding thing, which is a generalization. It's sort of a list, like a relaxation of the above notion, which is to say that I don't mind it as long as this list size, or rather the number of code words in the ball of radius delta, is not too large. Okay, and this not too large is typically captured by some L, by some parameter L, which denotes the list size. But you should mentally be thinking of it as saying that if someone told you that L was sort of polynomially large in the block length, in some sense, I want to say that is acceptable. Because in a typical scenario, the number of code words you're dealing with is like exponential. So as long as you can somehow give a significantly smaller bound on this list size, you sort of say that your code is list decodable. I mean, but of course, I'm just making a sort of a vague qualitative statement. So, but a formal thing would be to say that you fix the radius delta and the list size, and then you say that a code is delta comma L is decodable if any ball of radius delta centered around any point contains no more than L code words. Okay, and I don't know. So one of the things that we saw last time was that something being delta decodable was purely a function of what is the minimum distance of your code. Okay, so if your minimum distance was at least 2 delta, roughly, I mean, because of this strict greater than sort of stuff, if it was at least 2 delta, this immediately tells you that your code is delta decodable. Okay, And something that we saw last time, which was to somehow justify the fact that list decodable codes are pseudo-random objects, was that if you pick up a code of this rate, which is 1 minus HQ of n, this HQ of n is basically the exponent for the ball size. Okay, and it's related to the entropy function in the limit, but the actual function is not relevant. I mean, it basically tries to capture how large is a Hamming ball in this world. Okay, and it basically says that no, if you pick a random code of rate a little smaller than this, it will actually be delta comma L list decodable with very high probability. Okay, and it turns out that this number is also the right number in the sense that rates like a little beyond that is not achievable, in the sense that you can't expect a code that has rate, and I'm shoving some smaller factors under the run to say the word codes significantly larger than one minus HQ contains more than L code words. Okay, we didn't really see the proof, but I'm just telling you. So this allows us to basically say that in some sense the rate we should be aiming for is this quantity, and sometimes this quantity is also called the list decoding capacity. In the sense that, so sometimes it depends on how you want to think of it. This is like saying that you fix a delta, you say I want list size to be small, and you're asking how large can my rate be. The other way of looking at it might also be maybe you have a particular rate of interest and you have a particular list size, and you might want to know how much delta can I tolerate. Up till what radius can I somehow say that the list size is going to be at most? The function will be will be different. And something that we saw last time, but I think and the proof I was like a little unclear about certain things, called the Johnson bound. So I want to revisit the proof in this lecture, which was a Johnson bound is a way of somehow telling you that if you have a guarantee of the minimum distance of a code, you immediately have some list decoding guarantee as well. Okay, so it says that if your minimum distance is very large, in the sense that it's like 1 minus epsilon, then like it is also what did I mess up? I should have written 1 minus root epsilon. So 1 minus root epsilon comma So thanks. Okay, good. So okay, so the Johnson bound is what we want to show. And in fact, I'll sort of fix epsilon prime to be equal to 2 square root epsilon and prove the Johnson bound where, I mean, this and this is what I'm calling epsilon prime. Okay. Now, so this is like going to say that a ball of radius 1 minus 2 root epsilon does not have too many code words. Now, obviously, if I increase this 2 root epsilon to 100 root epsilon, that's a smaller ball. So, of course, it will have only fewer code words. Okay. So, last time I proved it for 100, but I'm going to do it for 2. I let you stare at the calculation to figure out how small can you make this 2. Okay, and the spoiler is that you can make this 2 like square root. You can make it square root of 2 epsilon in the whole proof, but we will see the...
Meaning the 2 can be pushed under the...
Yeah, so in some sense, the right answer is like epsilon prime equals square root of 2 epsilon. But we will do it for 2 epsilon because it just, calculations are just easier. Okay, and I'm going to assume...
These things are very significant.
With respect to what I'm going to say with the Reed-Solomon codes. Yeah. So the Johnson radius is square root of 2 epsilon. The thing, and anyway, I'll get to that. Okay. Assume on the contrary that some Hamming ball has at least 2 over square root epsilon code words. And by some Hamming ball, I mean some Hamming ball of radius 1 minus epsilon prime. I should have said of radius 1 minus epsilon prime has this many code words. Okay. We're going to use the same intuition. We're going to write this inclusion-exclusion calculation. But I'm going to sort of, it may be the case that I have lots of code words in this ball. I'm going to fix exactly 2 by root epsilon of them and deal with those. Okay. So fix y1 through yt as t of these code words, where for t actually equal to 2 square root, 2 by square root epsilon. I should probably put floors and fields or something, but I am not doing that. Okay. I think last time I just worked with a large T and suddenly it was like there was a negative number that was showing up, which bothered me in the end. So anyway, okay. So now let's do the same thing. I'm going to define AI to be the set of all coordinates J such that the received words jth coordinate is equal to the ith code words jth coordinate. Okay, I hope this is clear. So each code word has n hat coordinates, and you're basically looking at what is my agreement of the received word with the ith code word. So there is a certain set of coordinates that it agrees on. So that's what this AI is capturing. And we are basically going to
I goes from 1 to t.
Yeah, so this I is going from 1 all the way to t. So this is the set AI that is defined. And I want to know what is the size of this union. Okay. On one hand, of course, this can be no larger than n hat, because it's a subset of coordinates, all of these. But then by inclusion exclusion, this is at least as large as summation size of AI, I going from 1 through t, minus summation I less than j AI intersect j. Okay. And what do we know about the first term? Well, the first term is asking fix. Okay, let's look at one such AI. What's the size of that AI? Well, that's a statement about the agreement that the received word has with that specific code word. Now, this code word is in contention only because it's within this Hamming ball of radius 1 minus epsilon prime. So therefore, the agreement must be at least epsilon prime. Like it differs from R on only 1 minus epsilon prime coordinates. So therefore, it must agree with R on epsilon prime coordinates. There's a factor of n throughout outside. Okay, so this is going to be, let me write n hat outside. N hat times this is T epsilon prime. So that's the first term. Each of these AIs has size at least epsilon prime. What about the second term? This is like asking, take two different code words. R has some bunch of agreements with this code word. R has a bunch of agreements with this code words. What's the intersection size? Now, between two code words, because their distance was delta, which is like 1 minus epsilon, two different code words can agree in no more than epsilon fraction of places. So the common agreement with R can only be smaller than that. Okay. So therefore, this is going to be T squared choose 2 times epsilon. So this is a lower bound on the above term that you have.
Epsilon prime.
No, this is epsilon because this is a statement about the pairwise distance. So this is epsilon.
First one was
The first one was how much? Yeah, these are all in the ball around the received word R. Whereas the second one, I'm just taking a bound saying these were two code words of my code. They can agree at most at epsilon fraction of places. So it's at most epsilon.
1 minus epsilon was what is.
Yeah, the distance was 1 minus epsilon. Yeah.
Otherwise, I was thinking, why not?
Yeah. Yeah. Okay. And now